for you to get a better understanding of computer networks. So has any one of you have ever studied any computer networks courses before? Sorry, I'm not very good at using the Google Meeting, so I'm not sure if I can start a poll or something. Let's see. Not so far? Okay. So do you know there's a way I can just not let it just keep echoing this? All right, so if you have not studied it so far, I think this is a good time to have a basic understanding of networking. So networking has been a very long research topic or theme within the field of computer science. So it is basically a field that studies how we should connect computers together, right? So nowadays it's not only computers, but initially people just try to study like if we have different computers, we have different devices, how they should communicate with each other, and what if I want to exchange some data between them. But nowadays, we have more than computers. We have, mobile devices. We have those small sensors or the so-called IoT devices, and we have satellite. We have everything, and networking is now becoming a field that study how to just connecting everything together, and make this world a connected place. So if we talk about networking, some people might think that this is just physically connect things together, right? We just get a wire or use some wireless signals and make sure you can deliver something from one side to the other. But actually, this is more than that. Well, you actually have to manage the communication with some specific rules. Like you have to answer a lot of questions when you network. Like for example, you have a lot of opportunities to send data, but when exactly do you want to send it, right? Because it's not only you that is using this link. Usually, for example, if you're using Wi-Fi, you're sharing the link with many others. So you must have a rule to decide when people can send, when the other can send, when you should back off, right? You have to have this set of rules to make sure that everyone can have a fair share of the resource. And some other things, including like what should be the message format be, right? If you tell me something, it's just like speaking a language, right? So you have to speak something that I can understand, and I can speak something you can understand. So we have to make sure that this information over the network link has never been distorted, or you can always recover what I said. And we must speak the same language so you can understand what I want and you can respond properly so I can understand, right? And there's another important question, for example, that is how to reach others. You know that internet nowadays is very huge, right? You want to send a message to some of your friends in Asia, and definitely there's not a single hub that you can transmit data directly from your computer to his or her computer. So there's many intermediate steps that help you to find where's your destination. So all these procedures, they are all of the research fields of the computer networking. So we have to answer all these questions in computer networking research for sure. So so in terms of these rules, and one very important concept is called protocol. So we make an analogy here that in our daily communication, right, we usually have some socially, agreed rules when we talk to each other. Like say you say hi, I also say hi, and then you ask me a specific question, and I can answer back according to what you answer, right? So if you are talking in English, I can respond in English. If we both speak Spanish, we can talk in Spanish. And similarly, in networking, you have to make sure that the sender and the receiver, they are both talking in a specific language or set of rules or standard, which what we call protocol. So this is very important. So by understanding protocol, we basically understand that what is the basic units that control such rules and standards. And this is very important for us to understand the following contents. So let's say in this example here, the computer A sends some specific request to computer B. And if computer B understands this protocol, and then it can respond with a specific response. And this specific response can be processed by computer A, and you can further start the file transmission, et cetera, et cetera. So you have to make sure that both parties speak the same language, which is the protocol in our computer networks.
And there are so many protocols in the computer networks, and generally they will define format and also order of the messages that are sent and received among the network entities. So people can understand, different computers or different devices can understand each other, and they can take the proper action when you receive something. For example, if this specific message, tell me that, well, the previous message has not been received, please retransmit. Then if I'm also using the same protocol, I see that there's the message in this specific format I can understand, then I will properly send a retransmission back to the other side. So the other side can, next time it can say, well, this time I receive it. So I can start to send the next message because the previously has been successfully acknowledged, right? So the protocols will define what to send, basically what the message will look like, and also how to react. So if I receive a retransmission request, I should retransmit the previous data. So in reality, in the real net, so the so-called reliability, right? Then the protocol should include some features that ask for retransmission, as I mentioned before. So this rule should be included, right? So probably one protocol will handle this one, and some other protocol will handle, for example, if I want to reach you, if you're in Asia, how I can reach out to you. So there should be some protocol that decide what's the best route that I can find you. So there are many different protocols working counter. So if you're interested, definitely go out and look for more protocols that exist. So any questions so far? All right, so if not, I will continue to introduce a real case study, which is the internet, right? We have, I'm not sure, because when I was young, the internet was just starting to roll out. And at that time, sometimes it's really slow and it's really difficult to have a decent connection so you can watch video or whatever. But now, I mean, when you are born, the internet is there, and there are so many different good quality services provided by the internet, and our lives has been benefit tremendously by the internet. So it's better that we take a look at how internet is being architected and what are the components within the internet. So the first thing is what we call the network edge. So by the word edge, you can understand that we were referring to something that's on the edge of the network. So it's on the very edge. So we can see we have the phone devices, we have the computers, we have smartphones, we have laptops, desktop, or servers. And all these are considered network edge. So this is on the very edge, very end of the network. So servers nowadays, I think it was not the case like 10 years before, but nowadays, so many people are using the so-called data centers. So data centers, you can think of that the big corporation like Amazon, Google, they have their own server cluster, right? There's a specific place in their corporation that hosts thousands or even tens of thousands of servers there. And other corporation can rent their services, which was so-called the cloud computing. So basically, the big corporation have this kind of server cluster, which is used or shared by all these other services. So that's basically cloud computing, right? And so nowadays, the servers are usually in the data centers, not hosted by every single company, because that would be too expensive. So they'd rather just rent the service from other cloud service providers like Amazon, AWS. So the second part of the internet is the so-called access networks or physical media. Because for the end devices, like for example, you took out your phone, right? You want to have the internet services. It's not likely that you will have a wired connection between your phone and internet. Usually you use something like Wi-Fi, like 5G. So this is the wireless communication. But if you're using a desktop, you still use Ethernet, and probably have used this before, right? You use Ethernet to connect the one port on the computer and the one port at home, so your desktop can have access to the internet. So this is the wired connection. So, but anyhow, there must be some kind of media for you to access the rest of the internet. So that's the access network. And then in the middle, we have the network core. As we mentioned, two nodes, they're very far away. So you must have some intermediate nodes that connect different parts of the network together, which are the routers. So the routers will receive the message from you and help you find who's the destination. Okay, so that's the routers that are sitting in the middle. So what's the protocol stack used in the internet? So we make another analogy here. So we think about the organization of air travel. So what if you want a end-to-end transfer of person plus the baggage? So the first thing is that you have to purchase a ticket, right? You have to logically have the access to the ticket, and then you have to check the baggage, right? And then you go to the gates, and then the runway takeoff, and finally there's the airplane routing in the middle, so you can have your airplane from location A to location B. And when you landed, you first go to the runway landing, and then you go to the gates to unload things, and then you claim all the baggages. And then if you still have some issues with the entire trip, you don't go to the gates or you don't go to the baggage. Instead, you use your ticket as the identification for the complaints. So there's different layers, a series of steps involving different kind of services, and each one is doing its own job. So this is quite similar to internet protocol stack. So we have a bunch of protocols that are providing different types of services for the internet. So usually what we have are so-called 5-layer architecture. So on the very top, we have the application. So for example, if I want to tell you that if I want to send an email to you, then I must follow the application protocol of email, right? I must write an email according to the email protocol. So the receiver, which is also running the email protocol, can understand what I write. Because what I write is not just the content, right? I also write what's the sender, what's the copy, what's the blind copy, etc. So I must write in a specific format that the receiver can understand. So that's the application protocol. And then the application protocol packet will be sent to so-called transport. Transport is basically end-to-end. So transport is responsible for example, retransmission so that the reliability is ensured. And transport is also responsible for something like rate control so that you don't overcrowd the network. So transport is more like running on both sender and receiver, so they talk to each other and make sure that you have some nice features such as reliability and rate control. And the network layer is basically a layer that handles all your routing, right? You probably have heard of IP. What is IP? IP is Internet Protocol. That's a specific protocol on the network layer used by Internet. Okay, so that's IP. So every single device in the Internet will be assigned an IP address. So this is like your home address. So when you try to reach out to someone else, you must have the destination's home address. So when you send a letter, for example, to one of your friends, you would just put the destination address of the receiver of your friend on the letterhead, right? So that's similar for internet. When you send the data to someone else, you must have the IP address of the receiver and you put it in the packet. And then all the routers, etc., will help you find where the destination is. It will route your specific packet to the destination. Okay, so that's the network layer or IP protocol that is being used in the internet. And then we also have the link layer, which is more like, for example, 5G. 5G is more or less a link layer. So it helps you to transfer data from one link to the neighbor. So this is different from network. Network is more like an overview. It's logically how I should reach out from destination A to destination B. The link layer is more like, it's more like a car provided by the local postal office. Link layer helps you to transfer a letter from your home to the postal office, and from the post office in location A to the post office in location B. That's link layer. Link layer basically handles every single delivery between the local two links, while the network is more like planning. If you want to transfer a data from location A to location B, which postal office I should go to first, and then which destination I should go to next. So it's more like a scheduling on the top of the every single link. And physical layer is more like the actual delivery man, just carry all the data over the wire or over the wireless links. So this is the internet protocol stack. So if we take a more direct look at that, whenever you have a message, this is an application message, and then you put it into a transport. You put so what happens in reality is that you put a so-called header onto that message. Header is just attached before the message. right? So this header will include some important information. For example, if the sender has received the acknowledgement, or if the sender wants the retransmission from the other side. So these are all included in the header. This is how the other side can handle that. And then you put it into the network layer. You just, for example, include all the IP address of the destination, IP address of yourself, and then you put it into the link layer. Link layer is more like for local transmission, okay? And then physically, it goes to the receiver. The receiver's link layer will first process the header of the link layer. And after processing, if the data is fine, it will forward everything to the network layer. And network layer will handle the packet and get rid of the network layer header and push the data to the transport layer, which will get rid of the header of the transport layer and put it into the application layer. So the receiver can successfully receive the message that the sender intended to send. So from the application's perspective, everything below will be transparent. But every protocol before, they work in concert to make sure that, for example, the data has been successfully delivered, the data has been reliable, the data rate does not like overcrowd or just overwhelm the network by controlling the data rate. So that's how the internet protocol works. So any questions so far? Yeah, please just raise any question if something is confusing and or you want to discuss more. Yeah, if it's nothing so far, I will try to continue with the next step, that what we are actually researching in the networking. So for example, for the previous internet things, this is it's a mixture of wired and wireless networks, right? And internet is definitely a wide area network. Wide area means that it covers a very large space. It's the network of networks. That's why it's called internet, right? So there are also some local area networks. For example, from in your office, in your school, you have a local area network that handles everything. So just one quick question for you to think about that. What is the difference, for example, when we do research, what is the major difference between a wired and a wireless network? So I'm not sure if I can get any answer from it. So if you want to have a try, you can provide some answers if you want. So yeah, think about it. From your own personal experience, what's the biggest difference between a wired and a wireless network? Yeah, any answers? Yeah, for example, just imagine that if you're using I'm not sure if you have used Ethernet before, but using Ethernet is definitely, most of times it will have higher throughput, and it's more reliable, right? Because it's wired. So in a wired network, you don't have to worry about that. You're contending with some other nodes. Yeah, I see an answer from Sophie. So a wired network involves some sort of physical connection, whereas a wireless network does not. I think that's a great answer. So basically, it means that if it's a physical connection, then it's, for example, you have a wired, right? So it's more difficult for others to interrupt the connection. So when you transmit some data from node A to node B, and it's usually more reliable and prone to any noises. On the other hand, because wireless network does not have any like physical connection, so it's very likely, for example, there are some noises, and then your wireless connection will be broken. So this will result in a very distinct feature for wireless network, that is the transmission failure rate is really high for the wireless. So you have to design all those kind of data recovery, data retransmission mechanism for the wireless networks. So that's one thing that for the wired network, you don't have to worry too much about that. I think that's a great point regarding the connection, physical and the wireless. And there's another point I can mention is that for the wireless network, usually what happens is that there are so many different people using the same channel, right? Using the same channel. So you have all these contentions because you have no idea what time will others start to send data. So it's very likely that you will conflict. So in terms of conflict, how could different people resolve the conflict? Do I just retransmit? Then if the other guy also retransmit, then it will keep colliding, right? So the research in this area try to make sure that you have some clever scheme. You just back off a little bit. When there's any collision, you will intelligently do some randomness and back off. So make sure that different hosts, when they do the retransmission, and the next time, the probability of collision will decrease greatly. So this is also another thing that that's very, very interesting in terms of the wired versus wireless. And so that's pretty much, and also some other differences in terms of the throughput, etc. If you're interested, you can definitely take a look. And there are different networks to research for sure. So traditionally, people started from internet, from 2G, 3G, and people study Wi-Fi and also some ad hoc networks, which means that the network's nodes can come and by very often. And most recently, there are some very interesting topics. One is the data center networking. This actually was very popular like 7 years ago, 8 years ago, but now it's kind of finalized because people have found some great solutions to data center networking. But it was a very interesting topic that because in the data center, I mentioned there can be thousands or even tens of thousands of servers there. So how I can make sure that they're interconnected with a great structure, how to make sure that their protocol running in the data center network, because you cannot simply reuse the internet protocol. That will be insufficient for specific context where every single data center server being hosted within this data center. So how to make sure that these computers, they're interconnected correctly. And also some IoT related stuff, like we have millions of IoT devices, sensors. How can we interconnect them with low power? Because IoT are very power hungry. Sorry, they are very power constrained, so you don't want to consume too much power on these devices. And 5G, 4G, or even satellite network. And probably you have used Starlink before. That's the satellite network, right? And with so many different networks, we have different aspects to study on these networks. Like for example, by the way, these network protocols are usually being standardized by some specification. So there will be an official organization that they will host meetings like annually or even quarterly to discuss whether they want to make some change on the protocol or whether they want to make a new version of the protocol. So to continuously improve it, make sure it's up to date, or just completely overturn them and make a new version so that, for example, from Wi-Fi 4 to Wi-Fi 5 to Wi-Fi 6, these kind of things. And this specification, as I mentioned, will define the message format and behavior of different protocols. Let's say for 5G, 4G, there's an organization called 3GPP. Wi-Fi is being defined by IEEE, and internet protocols, most of them are being defined by RFC. So there are different experts from different areas. They just go to these conferences and they decide what should be the next for these protocols. So the purpose of these meetings, of course, is that whenever you have a protocol specification, so if you're, for example, Ericsson, or if you're HP, you want to make a different device. You want to make sure that they can talk to each other. They can connect to 5G base stations. Then you must speak the correct language. So they just simply have to refer to these protocols and then implement these protocols within their products. So their products will be specification compliant, and they can publish them to the public, to the market. And whenever a customer purchased it, you can make sure that it will connect to the others correctly. So in terms of these networks, there are different aspects that we researchers usually focus on, including the performance. For example, whether the throughput is high or low. Throughput refers to data rate. So for example, if you're transmitting like 100 megabytes per second or 500 megabytes per second, can we achieve more? This is throughput. And also latency. For example, if I want to deliver data from my computer to a data center, will it cost 1 second? Can I improve it to like 0.5 seconds, etc.? These kind of things. This is basically we want to have a lower delay for this delivery. Also the reliability. We want to make sure that if a single message is failed, or even worse, for example, the Wi-Fi, your Wi-Fi box just breaks down. Can we still make sure that the device has some sort of network connectivity and recover from such failures? And there are also some security-related works where we try to find out if the protocol has some security issues, so the attacker can leverage that. For example, the attacker can forge a message and insert it into the network and make your computer crash, right? So is that case possible? This is especially an issue for wireless network, because for the wireless network, it's public, right? So everyone can send some signals over the air. So it's very important for us to make sure the wireless connection is secure, so no one can actually forge anything over the air. If it's Ethernet, then it's harder to break in. It's not that easy to eavesdrop on the wired channel or to forge something inserted into the wired connection. But it's easier for the wireless networks. And some other things in terms of power consumption, like I said, the IoT devices. Nowadays, people are pushing it to the extreme that they're making some IoT devices that you just put them in the wild. They expect it to last for 3 years, even 5 years, without changing the battery. So it's very important to make sure the network communication can consume very little power to support such kind of use cases. And there are also many other works that try to design the applications based on the networks, like redesigning the application to fit the networks, or vice versa, to improve the networks for different applications. Also, some research works, they will focus on the operations, saying that if the network operator or the vendor, they correctly implement a protocol, if there's any issues with that, or if they charge the users correctly. So there are different things to study, but everyone is very interested. All right, so for the second half of our discussion, we'll move on to the 5G networks and talk about some of my recent researches in 5G. So if you have any questions, please ask now. All right, so I saw a question from Sophie. Is wired transmission more secure than wireless transmission? For example, would it be easier to intercept classified data being transmitted over a wireless network than it will be data were transmitted over a wire? I think that's a great question. You probably asked the question before I explained wired versus wireless. And this is a great point. For the wired, usually I'm not sure if you have heard of a word called a threat model. So when researchers study a specific security issue, they have to make some assumptions. For example, what the attacker can do, what the attacker cannot do. That's so-called threat model. So the model of the attacker. So they want to model the behavior of or the privilege of the attacker. So if it's a wired network, usually the threat model is very strong. Let's say the attacker is some kind of insider attacker that has the access to a specific router, so they can do some internal things, which usually is not the case. Meanwhile, for the wireless networks, for Wi-Fi, for 4G, 5G, and the papers, they usually assume that the network, the attacker does not have any elevated privilege. What they do is that they just you purchase a specialized hardware and just sitting in the wild and place that hardware, and that hardware can just receive all these different kind of signals and also forge some signals into the air and send to the base station or send to the Wi-Fi AP or whatever. So usually the threat model for the wireless networks is usually much weaker or much easier to achieve to some extent. So yeah, I agree with what you just mentioned, that it will be easier to intercept the data over a wireless network. So that's so the result of that is that it's very important. For example, we encrypt every single message that is transferred between the device and the base station, right? So for wireless, or for the make sure the classified data will be encrypted and be properly put a signature together with the data, so that make sure that no one is attempting to change or tamper the data being transferred over the wireless link. Yeah, I hope that answers the question, and I think that's a great point. Yeah. Any other questions so far? All right, cool. So let's move on to talk about the 5G a little bit. So actually, 5G research is nowadays still very important. Although we have seen the 5G has rolled out for several years, I guess, but 5G has so many different components and so many different operational modes. Not all of them have been put into commercial use so far. And also there's still something that's being planned in future, also for the future 6G. So the research community is very actively focusing on the area, try to improve different aspects of 5G. The first thing we want to do is try to understand the 5G architecture a little bit better. So here's a note that this figure is what I copied from a 4G architecture, but in 5G that's basically similar. So I just reuse it because I think this picture is very well drawn. So in 5G, what we have is first so-called UE. UE is short for user equipment. So the smartphones that we are using daily are if they have 5G capacity, then they're UEs. And you probably have also used some like iWatch, like smart watches. If they have 5G connectivity, then they are also UE. So UE is basically is a terminology for any device that is capable of 5G connectivity. So we have this one as our edge, right? This is edge devices. And then we have the so-called Inobi. Inobi is basically a term that is very, I'm not sure why they call it this one. No one else outside of the community can understand it. But basically, these are just base stations. Okay, you just deploy. The operators, they will purchase the base stations from the vendors, and then they just try to deploy them in the city, in the wild. And actually, if you go online, there are multiple websites you can search for where AT&T or T-Mobile deploy their base stations across the country. And these base stations are used to cover the geographical areas and provide services for UEs. So these base stations are usually very powerful, though they can transmit the data over a very long range, and they can also hear from the devices that is being transmitted over a long range. And usually the deployment is kind of dense, so that when user moves, you always can find a proper base station to connect to. So there's one critique over 5G, that is 5G is a little bit shorter range compared to 4G because it increased the power, it tries to transmit more data, but the trade-off is that the range is not very long. So actually 5G, you have to deploy more base stations in a denser manner to make sure that it has the similar coverage compared to 4G. So yeah, that's so the coverage is very important, especially for operators. They want to make money. They want to make sure that their users don't complain about the coverage of the 5G or 4G. And then these base stations, they are connected to so-called backhaul network. So you can think of it as some routers. They just route the data from the base stations to what's so-called mobile core. So this core is very important. This core, usually one city will have one core. Or, I'm not sure about the current practice, but at least several years ago, this is a citywide stuff. So every city will have a mobile core. It basically collects the data from all the base stations, and it will basically forward all the data from base station to the internet. And then if there's any data from internet to the user device, it will try to route this data to correct base station and correctly deliver to the user device. So this is the core. But the core is not only that. The core is also a very critical component that, for example, has all the credentials of the devices. Because not everyone can use the base station, right? You have to pay for that. So when you, for example, want to empower your 5G device with 5G network, you have to go to AT&T, say, hey, I want to purchase a SIM card, and I want to purchase a data plan. So this data plan will actually be stored within the mobile core. And whenever your phone starts, you must attach the SIM card, or nowadays it's very advanced, right? You have the eSIM, so the electronic SIM cards. So you basically have those SIM cards enabled, and then your UE will just send the credentials that's being stored within your SIM card to the mobile core. The mobile core will verify and see, oh, this user has already purchased something, and it is authorized to connect to the network. And there are some like authorization procedure between the devices and the mobile core. And after that, the mobile core will tell the base stations that, well, this device is okay. You can start to serve for these user devices now. So the mobile core is not only a router between the base stations and the internet. It's also some very critical component that verifies the devices and store the information of devices. So this is mobile core. So it's a very critical component in 5G. And then we have the backbone, which is the internet. So this is the basic architecture. So some critical components is UE, base stations, and also the mobile core. So there are different protocols running between all these kind of devices. I don't think you have to understand them, but just a basic understanding will be enough. So I mentioned before that you have to verify your identity. So the identity is happening between the UE and the core, right? So this is the NNS protocol that will carry all these control messages. So all the control-related messages in networking, we call them control plane. Okay, we call them control plane. Just basically a part that manages all the control-related messages. And data plane is basically to carry the user data. So we have the NAS protocol communicating with the core for the verification, authorization, etc. And we have the RRC protocol. This is between the device and the base station. So this is basically used to control all the radio, like which radio you're connecting to. And if you move, the RRC will help you move to a new base station. So that's RRC. And then we have multiple data plane protocols to handle all the data. So for every single data, it will go through all these protocols to make sure the data transmission is reliable, because we mentioned before, the wireless transmission is very unreliable. So you also need some retransmission in these protocols. And also, these protocols are responsible for encryption, for data management, etc. So we basically have two control plane protocols to control the base, for the base stations to control you, and also for the core to authorize you. And we have all these data plane protocols to facilitate the data transfer, to ensure reliability, and to ensure this retransmission and encryption, etc. So you can think of that whenever for example, you are trying to visit a web page, the web page packets will be passed into PDCP, and then goes all the way down to the physical layer and wirelessly transmitted to the base station, and goes all the way up to PDCP and goes to the core. And these protocols will make sure that this transmission is reliable, is encrypted, so that no one can, just intercept the classified information. So that's basically 5G architecture and the 5G protocol. So if you're interested, definitely you can search for every single protocol online. There's some very detailed notes regarding this protocol. All right, so any other question for 5G? All right, so Haiyan answers the question. InnoB stations only cover 5G coverage, or can it host multiple generations, at least 4G? I think that's a great question. So from my understanding, nowadays, if you purchased a 5G base station, that's basically 5G only. Because the point is that these base stations, what's the biggest difference between 4G and 5G? Actually, you might be interested in this. From my understanding, the biggest difference between 4G and 5G is on the physical layer. So their radio are very different. As I mentioned, 5G is more powerful. The physical layer is more powerful than 4G, so it can transmit more data simultaneously. And in the meantime, it sacrifices a little bit of range. So the 5G base station and 4G base station, their hardware will be very different. So here, as I mentioned, this InnoB is actually 4G base station. Actually, 5G base station will be called GNOB. So usually, 5G GNOB and InnoB, they're different hardware, so they're separate. A single base station cannot serve both 4G and 5G. But there's one interesting property of 5G and 4G, that is whenever you have a phone device. So actually, this is before 5G, so this is an interesting story. You might notice that over the year, even if you're always using 4G, but you might notice that the throughput or the data rate of 4G has increased tremendously over the past several years before 5G rolls out. Why is that? It's because 4G is actually keep improving itself. As I mentioned, the 3GPP is in charge of the 4G specification, so they just have these meetings to improve it over the time. Like, for example, one very critical technology is that a single device, previously, they can only connect to one single 4G base station. But now, they have developed some technology that one single device can connect to 2 or even 3 base stations and simultaneously transmit and receive data from them. So it's actually double or even triple the throughput. So previously, it might be 100 Mbps, but now it can be 300. So this is the same case for 5G. So now the 5G rolls out, even if it's separate from 4G, but there are some specific technology from 3GPP. They define that a single device, if it's capable of 5G and 4G, it's actually capable of connecting to both technology and transmit data over both technologies simultaneously. So you can gain like double the throughput or even triple the throughput. I think they even have some technology that you can connect to like 5, even 10 base stations, although it is not very common because you usually don't have so many base stations in your area. But theoretically, you can actually connect to, I think, 12 or even more base stations simultaneously. So that could be a very strong power for your data rate. Yeah, I hope that answers the question. So any other questions? Okay, great. So now we have a basic understanding of 5G and its architecture and its control and data plane. Let's look at some issues in 5G that I previously worked out over the past few years, and also some solutions that I have proposed. So this might be difficult, so I try to explain it in plain words. And so if you have any questions, as always, just stop me and we can discuss more. So the first thing we want to study is that whether 5G is fast enough. So we want to see, let's say, if I have some, you know that there are some very latency stringent applications, right? So one application claimed to be supported by 5G is so-called AR/VR. So you wear a glass and you can play AR, you can play VR over the 5G links because it has such a high throughput. So you can stream all these videos to the glass or to the headsets, and you can watch VR, you can watch 360 videos when the other side is streaming. So this is the so-called this is the claimed application that can be supported by 5G. So what we did is that we tried to collect some real traces, and we did an empirical study over the major US mobile carriers to see if 5G is indeed promising. So what we do is that we write our own VR application. So over the headset, we are trying to stream some like a VR application. So when your head moves, so this is what you see within the headset is that you move your head and you see a different angle. So the server is processing all the video frames and streaming it back to the device. And we also study the specification regarding latency, regarding all these procedures from 3GPP, and we write our own application, try to gauge the critical information from the phone devices so we can analyze it and try to see how much time it will take for a VR to react. Because what's the most critical matrix? It's basically the time you move your head all the way to the time that you actually see the corresponding frame, right? So you have to make sure that when you move the head, you can quickly see this direction, this angle. You move it, you see the angle again. So if this time latency is very, very long, then eventually you will suffer from, it just doesn't feel good, right? You will feel dizzy and it doesn't feel natural at all. So our finding shows that the intuition that the downlink incurs high latency is not true, because intuitively, if you want to stream some VR videos back to your glasses, you might think that this video streaming is very high throughput. 5G might not be able to support that, but we find out that this is not true at all, because as we mentioned, 5G has increased so many bandwidth, has increased so many technologies, like we can connect to multiple cells. The result is that the downlink means from the server to our glasses, to our devices. So the downlink is not an issue, but actually the uplink is a bottleneck for the entire transmission. The uplink means that because when you move the head, right, the headset must capture the motion and send it to the server for processing. This time, even if this is a very small sensory data, just basically the head motion, but it will take 66 to 78% of the latency. Surprising, right? So why is this the case? We find out that there are multiple issues for this uplink data transmission. The first is that whenever you try to send some data from your glass, from your headset to the base station, you have to go through a very long scheduling procedure. Scheduling means that you have to wait until the base station allows you to send something. Why is this the case? Because in Wi-Fi, and just another knowledge is that Wi-Fi doesn't need that. Wi-Fi, when you want to send something, you just send it out. If it's collide, then you have some backup mechanism to send it again. But for Wi-Fi, you don't have to wait. You just send out something. But for 5G, you have to wait until base station tells you that you can send data, then you can send some data out. So why this is the case is because 5G, as we know, it's a licensed channel. So different operators, they actually purchase the right to use that specific wireless channel. So it means that you cannot send it by your own intention, right? And usually this will result in some waste of the channel resource. So you can only send some data until the base station authorizes you to send some data. So this scheduling is an issue. It will incur a very long interaction between the UE and also the base station before you can actually send out the uplink data. And on the other hand, as we mentioned, the retransmission is also another issue that we have to go through multiple rounds in order to send out the sensoring, the motion sensor data. And another issue that is interesting is power saving. So the device doesn't want to send data all the time. It doesn't want to keep awake all the time, because whenever you keep awake, you have to listen to all the channels, and this will incur a lot of power consumption. So you don't want a battery to run out so quickly. So the result is that 5G has designed some mechanism to make sure that periodically the device will go to the sleep mode, during which you cannot do anything. So if you want to send out something during this sleep mode, you cannot. You have to wait until the device wakes up. So that's also another latency source for the uplink. So we designed some solution try to tackle these issues. So I think in research, especially in system and networking research, a very important rule of thumb is that if you can, don't change the underlying protocol. So if you can handle things on the application, it's easier. Why? Because we mentioned if you want to change or update a protocol, if you want to build a prototype, it's fine. But if you really want to impact the community, you want to impact some real application, it will be tough because they cannot change the protocol. You have to go through all these kind of meetings. Usually takes years before your idea can be realized. And also your idea might not be accepted at all, right? So the best solution is to do it in the application. So what our solution tried to do was that we try to send out some small packets to bypass all these previous restrictions. So how to do that? You have scheduling, right? But if we send out some small packets first, then we can pre-allocate some resource from the base station that can be used by the actual data. So we have retransmission, right? If we send out more small packets, it will trigger the retransmission quicker, so we can quickly recover from the bad channel quality. We have power saving, right? So if we send some small packets beforehand, we can wake up the device, so it doesn't have to wait all these kind of long period before the sleep mode ends. We can pre-exit this kind of sleep mode by sending out some small packets first. So just using this simple idea, we are able to increase reduce the latency for this VR application. So this is on the left is legacy, on the right is LRP, which is our solution. So you can see when you move your head, the right view is definitely smoother compared to the left one. So you can feel that there's some laggy scenes result from the long latency. But on the right-hand side, it's pretty smooth. So this is due to the latency reduction produced by our solution. So this is the first part. We talk about the latency of that. So any questions? All right, I will quickly wrap up the next two projects. So the second project is regarding the vulnerability or security of 5G. So you might have already learned some crypto basics, but I can give you a brief introduction to that. Is that if you want to make sure a data is secure over the transmission, then the first thing you have to do is to encrypt it. Usually what you do is that you will share a key between the sender and the receiver, and then you use some like complicated encryption algorithm to make sure that anyone without a key cannot decrypt the data. So even if it's a wireless link, everyone can eavesdrop on the channel, they cannot actually decrypt the data. They don't understand what's being transmitted. And then a second very important part is to attach an integrity code with the encrypted data. So it's also the same. Both sides, they share a key, and then you calculate somewhat like a hash value. So you probably have heard of it. You just calculate a crypto hash based on the encrypted data and the key. And you generate an integrity code and attach it and send it together with your encrypted data to the receiver. So the receiver can do two things. First, the receiver will use the key to calculate the same crypto hash on the encrypted data to verify if the integrity code calculated and received they match each other or not. If they match, it means that the encrypted data has not been tampered by any attacker. Right? If they don't match, it means that, well, either integrity code or the encrypted data has been changed over the transmission. So this data is not reliable. I cannot trust this data. So the integrity code will make sure it's the data received is intact, hasn't been changed by attacker. And encryption makes sure that even if anyone else eavesdrop on a channel, they cannot understand what's actually being transmitted over the air. But the vulnerability here is that because 5G has so much data to transmit over the air, so the integrity protection, so this integrity code is actually optional. So it means that most of the time, this one doesn't exist. And then if we simply have the encrypted data, and then the attacker can actually forge data, even if it's encryption. So there are some tricks you might be interested. If it's encrypted, why I can still forge some data, but there's some way you can actually forge some encrypted data. If you're interested, you can search online. The conclusion here is that as long as you don't have the integrity code, the attacker can forge some data to the sender receiver, and they cannot actually distinguish it between the legitimate copy and a forged copy. This is due to the overhead, because calculating an integrity code is very high cost. And imagine that you have so many data, you cannot process them in time. So usually they just don't do it. Encryption is somehow much easier. So they just make it mandatory. So you must encrypt the data. And due to such kind of overhead, we have an insight that instead of trying to add such kind of integrity protection, can we do something that complementary, that we just, on the receiver side, can we do some detection and mitigation? Can we detect whether a data being received is actually authenticated, or this is more like a malicious data? And then if we find out something suspicious, we can do some mitigation to kick out the attacker. That's what we do. But you know that we don't have such integrity code for the checking, but we can actually check, for example, whether signals over the air looks like from a actual base station or from another node. Because base stations, their signals have their own signature, right? Even if they don't add a digital signature, like based on the encrypted data, but their signals are very unique. They're from a same location, they're from a same direction, they're from a same distance if you're not moving very fast. So you can capture the signal and understand whether this signals there looks legitimate or not. And then you inspect it. And finally, if you find out something, just consider any abnormal behavior as potential attack to mitigate it. So the problem here is that how we can capture the signal. As similar as before, we don't want to change the device, right? We don't want to say, well, we change the entire device. That could be very difficult. So what we do is that our solution builds a separate node, which we call security hub. So as long as you place it near your phone device, it can actually capture all the signals that are being delivered to your device. For example, your smartphone from the base station. You can actually capture everything within this security hub, and then you can use this security hub to analyze all these signaling messages. And then you can mitigate it by switching the device to another base station. So as we mentioned before, every single device will connect it to a base station, right? So if you move from one base station to another, it will be very difficult for the attacker to track where it actually moved to, because this entire movement procedure is encrypted. So usually they will send you a handover command. Handover means from one base station to another, and this command is encrypted. So the attacker cannot track what's the new base station that you actually moved to. So we can use this security hub to send some signals and force the device to switch to a new base station so that the attacker will lose track of where our victim device is. So by these two steps, we first capture, then analysis, then we just force the device to transfer to a new base station. We can make sure the attacker will be eluded by our scheme. And the final part of 5G is that we find out that 5G is lack of failure recovery. So I will quickly go through that. So the problem here is that whenever a failure happens, the 5G cannot quickly recover because it lacks the global view. So for the entire 5G base station, device, etc., so they don't understand which part is going wrong, especially when there's failure. It's really tough for them to talk to each other, right? Because it's already failed. So there's no information channel that can be establish this kind of message exchange between them. So usually what happens is that in reality, they just do some blind trying. So they try this, they try that to see if it works. If it works, it's good. If it doesn't work, they just don't know how to do it. They just abort. And we have designed a very clever solution using the SIM card. So as we mentioned, you always need a SIM card to get access to the network. But you might not know is that SIM card is a very powerful microcomputer.
So you can actually load some Java applets within this SIM card and do a lot of stuff. You can use this applets to communicate with the kernel, or basically with your operating system on your phone devices. You can communicate with the base stations. There are some side channels to do that. You can communicate with the core. So we design a solution. We write a Java application on a SIM card so it can communicate with different parties, and it captures all the necessary information to diagnose which part is actually wrong whenever there's a failure. And based on this information, it can perform some designated resets to recover from the failure. It's no longer the clueless retry. So I probably just give you some idea of how powerful a SIM card is, and it's actually a very interesting research direction. All right, so any questions? All right, so since we are running out of time, so let me quickly wrap up the final part. Hopefully it will just take 2 more minutes. So what should you, if you're interested in networking research, what are we supposed to do? So I have several reasons that I think of that might be very interesting for networking research. First is that there are so many emerging networks for us to study, including satellite networks like 6G and beyond, like people are planning and talking about this a lot. And also the vehicle networks. So we talk about the autonomous driving, but actually it's very important for these vehicles to talk to each other or talk to the cloud, to the infrastructure. And if you're more a system building guy, doing networking research gives you a lot of opportunity to build some real prototypes, and you can see those robots or just vehicles talk to each other with your actual solution there. And also, it's very interesting to apply networking to some other areas like applications or systems. So recently, we've seen a lot of networking for agriculture, for underwater communication, for healthcare. Like you want to transmit its data with some in-body sensors. You put some sensors within the human's body, and you still wanted to communicate with your phone device, smartphone. And these are very exciting areas that people are working on. So usually, what I suggest is that I think almost for every single undergrad program, they will have a mandatory networking course for you to study. So this is a great opportunity for you to learn the basic internet protocol stack. As I mentioned before, we have all those protocol stacks, especially TCP and IP. TCP is for reliable transfer, IP is for routing. So these are 2 core pillars for the internet nowadays. And when you go to graduate program, there's usually some graduate networking courses where you can read papers regarding the networking research and learn the specifications and read those and to understand it better. And yeah, this is more a system towards this networking research more towards the system side, right? It's not more like algorithm. There are indeed algorithms, but most of the time you will have some hands-on experience. So it's very important for you to have some solid programming basics, like understanding the protocols, that you have the ability to implement new ideas. And also sometimes you have to change within the system. Right? For example, you have to build an AR to test the network. You have to go into the details to see the signaling messages from 3GPP, from 5G. So you have to have the interest in hacking with the systems, like play with the Linux, Raspberry Pi, and this will make you a really strong networking researcher. All right, so that's pretty much all I have for today. Hopefully you have learned something from my talk, and hopefully if you're interested in computer networks, in computer networking research, definitely feel free to reach out to me. And yeah, this is my updated email. I just joined UCR, and yes, I'm very happy to be here today. And if you have any questions, just let me know.